Quantum computers are notoriously fragile. Every stray photon, thermal fluctuation, or crosstalk event can scramble a qubit state. That's why quantum error correction isn't just a nice-to-have. It's the absolute prerequisite for building fault-tolerant machines. But here's the catch. Traditional error correction relies on heavy classical post-processing and syndrome measurements that collapse superpositions, while machine learning approaches like quantum autoencoders suffer from vanishing gradients, barren plateaus, and training times that scale exponentially with network depth. Today, we're breaking down a new framework called Quantum Global Variational Learning, or QGVL, which slashes training time by up to 97%, eliminates convergence failures, and matches or exceeds theoretical stabilizer code performance. This isn't just an incremental tweak. It's a fundamental rethinking of how we parameterize quantum circuits for error correction. Let's start with the baseline. Quantum error correction works by encoding logical information into redundant physical states. The stabilizer formalism is the standard mathematical tool here. You define a code space using Pauli operators, measure stabilizer generators to get an error syndrome, and then apply a correction. It's elegant, but it requires classical feedback loops that introduce latency and additional noise. To bypass that, researchers turned to quantum machine learning. Specifically, dissipative quantum neural networks and their most famous variant, the quantum autoencoder. The idea is straightforward. Feed a noisy encoded state into a feed-forward quantum circuit, compress it into a smaller hidden layer, and let the network learn to reconstruct the original state. The trainable parameters are unitary matrices applied at each interlayer connection. But here's where it breaks down. In a standard QAE, every connection between layers requires its own local unitary matrix. As you scale up to correct more complex noise or use more physical qubits, the number of unitaries explodes. That parameter proliferation directly triggers the Barren Plateau phenomenon. The cost function landscape flattens, gradients vanish, and training either stalls at saddle points or converges to poor local minima. You end up needing dozens of random restarts just to get a single successful run, and the training time becomes completely intractable for anything beyond a handful of qubits. QGVL solves this by changing how we structure the interlayer mappings. Instead of distributing dozens of small, local unitaries across the network, QGVL uses a single, global unitary matrix per layer transition. Mathematically, if you have an input layer of m qubits and an output layer of n qubits, a standard QAE might require m plus n separate unitaries. QGVL replaces all of that with just two, one global encoder and one global decoder. The operation itself is clean. You take the input density matrix, tensor it with a register of fresh ancilla qubits initialized to 0, apply the global unitary to the combined system, and then perform a partial trace over the input layer to isolate the output. The key insight is that while each individual unitary in QGVL is larger, the total number of trainable parameters drops dramatically. And because the effective matrix dimension scales with the total qubit count across the layer boundary, the per-operation computational cost doesn't actually increase. You're just doing fewer, larger matrix multiplications instead of many smaller ones. Let's talk about how this network actually learns. The objective is to maximize fidelity between the network's output and the target noise-free state. Fidelity measures the overlap between two quantum states, defined as the square of the trace of the square root of the product of their density matrices. When dealing with pure states, this simplifies to the expectation value of the projector onto the target state. The loss function is simply 1 minus fidelity, averaged over the training dataset. To update the unitaries while preserving their mathematical structure, QGVL uses a stochastic gradient descent scheme that enforces unitarity at every step. Instead of updating the matrix directly, it applies an infinitesimal rotation via the matrix exponential. The update operator is derived from a commutator between the forward-propagated input state and the backward-propagated target state. This is essentially backpropagation, adapted for quantum circuits. Because QGVL drastically reduces the number of unitaries, the number of commutators you need to compute and average over the dataset drops proportionally. That's why the training time plummets. The optimizer used is Rectified Adam, which handles the complex valued gradients by using the norm of the gradient matrix as a secondary momentum term, effectively compressing the complex update into a real-valued scaling factor while preserving direction. So does this actually work in practice? The researchers tested QGVL across a range of noise models and code sizes. First, bitflip errors using repetition codes. For a 3-qubit system, QGVL learned to correct single-qubit flips with fidelity matching the theoretical stabilizer benchmark. They scaled up to 5, 7, and 9 qubits, and the fidelity consistently tracked or exceeded the stabilizer code performance across error rates up to 50%. Then they moved to depolarizing noise, which is far more realistic because it applies bit flips, phase flips, and bit phase flips with equal probability. They trained on the 5-qubit code, the Steen 7-qubit code, and the Shor 9-qubit code. The results were striking. QGVL autonomously discovered correction strategies that matched the theoretical limits of each code. Interestingly, with the Shor code, QGVL actually slightly outperformed the stabilizer benchmark. That's because the Shor code is degenerate, meaning multiple distinct error patterns map to the same correction operator. The neural network exploited this degeneracy to learn a broader set of correction, pathways that the rigid stabilizer formalism doesn't explicitly leverage. But the real breakthrough shows up when you introduce internal network noise. In real hardware, the gates themselves are noisy. When the researchers injected noise into the forward layers of the network, QGVL maintained high fidelity across a significantly broader parameter space than standard QAEs. By expanding the hidden layer from 1 qubit to 3 in a 5 to 3 to 5 architecture, they added redundancy that prevented catastrophic information loss when intermediate qubits were corrupted. The trade-off is a larger unitary matrix, but QGVL's parameter efficiency makes training these wider networks feasible, whereas QAEs would stall completely. Let's quantify the efficiency gains. Across multiple architectures, QGVL achieved a 100% training success rate, compared to 80 to 89% for QAEs. Training time dropped by 96% in 5-qubit systems. The standard deviation in training steps was under 2%, which tells us the optimizer isn't getting trapped in local minima. The Barren Plateau problem, which typically kills variational quantum algorithms as network depth increases, is effectively mitigated by reducing the parameter space. On the computational side, classical simulation of these circuits usually scales cubically with matrix dimension. A naive analysis might suggest that larger global matrices are more expensive, but in practice, classical simulators can't efficiently update sparse local blocks without expanding them to full dimension anyway. QGVL's global approach aligns perfectly with how matrix multiplication actually works on classical hardware, reducing the total number of operations while keeping the per-step cost manageable. The paper also demonstrates an exploratory mode, where the network isn't given a predefined code. Instead, it learns to project a single qubit into an optimal multi-qubit code space tailored to the specific noise channel. This is a massive step toward adaptive, hardware-native error correction that doesn't rely on manually designed stabilizers. Of course, there are limitations. The current implementations cap out around 9 physical qubits due to classical simulation constraints. Scaling to larger codes will require more efficient gradient estimation and better handling of complex valued optimization. But the trajectory is clear. By collapsing redundant local unitaries into global variational layers, QGVL transforms quantum error correction from a brittle, parameter-heavy optimization problem into a tractable, scalable training pipeline. If you're working with variational quantum algorithms, quantum machine learning, or fault-tolerant architecture design, this paper is a must-read. The shift from local to global parameterization could be the key to unlocking larger, more robust quantum error correction on near-term hardware. I've linked the original paper and supplementary materials in the description. Let me know in the comments how you think global variational methods will impact the broader quantum ML landscape. Thanks for watching and keep pushing the boundaries.